novel cyclizations. In fact, you know, organic chemists are really named reactions. There's no Williams reaction, unfortunately. They usually come attached with some, German name or something, right? And so this one's the Pawson-Kahn reaction, right? Pawson was the professor and Kahn was the graduate student. He actually got his name on this reaction. And that was done with cobalt years ago, cobalt carbonyl. So later, people found out you could use all kinds of metal carbonyl derivatives, and I show you two cases for this reaction. The intermolecular and the intramolecular case. In the first example, here's the alene and here's the alkyne, and you take the metal carbonyl, and now the bonds that are going to be made are all these dotted yellow lines. A bond here, and a bond here. And the carbonyl, C double bond O, comes from carbon monoxide that's bound to the metal. That's where that comes from. So this reaction pretty reliably always makes unsaturated cyclopentenones. The double bond up here that was part of the alene that was most substituted with two R groups remains intact. Right? Now what if you did this so that the two units were somehow tethered? That's what we call this. They're tethered together via carbon chain. So here's the alene and here's the alkyne, and again we apply the metal carbonyl and we form the dotted yellow lines as bonds, and now we make, well, you got it, two rings at once. One's a 6-membered, one's a 5-membered, right? And so I wrote down here some precedents for this and how this was used. The problem is that in all of the preceding work, the reaction was described as being used in fairly simple substrates. In other words, this tether that you could have here, it had a lot of carbons in it, but no functionality. It never had much functionality because if it had functionality, then the metal might go seek out the functionality in a Lewis acid, Lewis base reaction. And I know you've studied lots of those. Well, we hit the jackpot. And I'm not going to go through this. This is just something to impress you with how diligent the student is who did this work. He tried lots of different examples, and sure enough, here's our magic bullet. We chose the diiron monocarbonyl and N-methylene, N-methyl, morphine, and oxide, NMO, as the reagent that actually oxidizes one of the COs off. I'll show you a mechanism. But at any rate, even at minus 50 degrees, warming at room temperature, the reaction occurs and delivers a major and a minor cyclopentanone. And this one was by far the minor, because you see I've given ratios under here, 97 to 3, 92 to 8, 97 to 3. We get these ratios, obviously, by using HPLC. And so we know by integration of the area under the peak how much is there. And it always delivers this major isomer in far greater abundance than it does the minor one. And you can see the difference is that the R3 group is now alpha to the ketone, whereas here it's beta to the ketone. Okay, that I think will become clear as I go on to show you a mechanism for this. Because right now we don't know how this works, right? We've got a reaction, we've scoped it out, as they say. It looks pretty general. You can make some fairly complicated things, like you can see down here in this reaction. The question is, can we use it to make our natural product? Well, Akshay Shah was the guy that was doing this work, and he was an undergraduate at Syracuse University in upstate New York, or an undergraduate at Syracuse before coming to Indiana as a graduate student. And he started the process of studying all the examples I showed you on the last screen. And one day he came into my office and said, there's something strange about this reaction. Here's its reaction coordinate. He said, the starting material, the so-called alene, disappears steadily throughout the course of the reaction. In fact, by about 1 hour, 50 minutes later, it's all gone. And the product grows in, just as you would expect. But there's this material that just comes up quickly, and then as a steady state, it just stays in the reaction all the way to the end. And I don't know what that is. And he was curious enough to think, well, it's not garbage. I'm not going to throw it away. I'm going to isolate it and find out what it is. Right? this turned out to be hugely important to how we understand the reaction. I'm not going to talk too much about the kinetics, but I'll only say this. The Pawson-Kahn, as studied by Pawson and Kahn with cobalt, starts by a reaction of the cobalt with a triple bond, and that's known. And the order of the reaction is zero order in alkyne. Now, most of you probably aren't mathematicians, and you're not going to think about that too hard. But just let me tell you this. When you study kinetics of another reaction, and you examine the order of the reaction in alkyne concentration, as we did here, and it registers that it's second order, or in our case it was 1.6 in order, then that tells you it's a different mechanism. It's not going by the same pathway. And that was really the most significant thing that came out of these types of studies about mechanism. Well, ultimately, this material, this tiny amount of material turned out to be an iron metallocycle. And he isolated it, and he put it back in the reaction with no starting iron carbonyl, and added more alkyne, and it continued and made more product. So, in the end, then, we studied all types of other allenes with this diiron carbonyl. And we figured out, well, one day we got one that was a crystal, and we could get an X-ray on it. And here's that example. The naphthalene is a substituent. The iron carbonyl, no added alkyne, no triple bond in there at all to react, makes a three-membered iron metallocycle. And there you see it. And of course, here's the iron right here in this now stable structure. A reaction-competent intermediate that we've just discovered. The first time anybody's discovered a ferrocyclopropane as the intermediate in a reaction. So this led us to discover even more three-membered rings containing iron and how they might react further to give our 2 + 2 + 1 couple cycle relation. We studied the mechanism. Now this is going to be pretty deep. I'm wading in here, and here's the iron. Here's this reaction-competent iron metallocycle, right? And we had two pathways. I dreamed these up myself. I said, pathway 1, we could lose one of these carbon monoxides because right now the iron, all around the iron, it's saturated, we call it. It's an 18-electron complex if you've taken your inorganic chemistry. And then there's nothing else that can bind to the iron. So you have to lose at least one CO to make room to bind anything else. So I thought maybe one CO just up and left. After all, carbon monoxide could go up the hood. And then it could bind the triple bond. And then it could do an alkene insertion that would make a 5-membered iron-containing ring. And then it could do a CO insertion that would make a 6-membered ring containing this ketone. And then that could reductively eliminate and give a product. That was one pathway. The other pathway starts down here. It says the first thing that happens is that there's the insertion of the CO. That makes a 4-membered ring right here that contains the ketone. And now that already opens up an opportunity to bind in a vacant coordination site with a triple bond to give this material. And now that could go on and give the same product. Well, that goes on to the end, right? And we didn't know which one of these pathways was more viable. So we went to a colleague whose job it is to do computational chemistry, and he just does calculations. And what we found out was that that 4-membered ring right there, that's the one right here. You notice that going from here to there is uphill by 32.7 kilocalories per mole. And our calculations say it's because this 4-membered ring is extremely strained. So we thought, well, that's pretty unlikely. And then he did another calculation that said losing a CO as CO2 because we have the morpholine N oxide, there's its structure in there. There's an oxidation reaction, and whenever you lose a particle like that, carbon dioxide is really stable. That's a benefit. We gain 50.6 kilocalories downhill in stability, right? So that's the driving force for this reaction right there. We lose one CO and that becomes a vacant site for now binding other things, including solvent like tetrahydrofuran. But that's almost energy neutral. and then the THF can come off there again. And ultimately, of course, that means we're gonna bind to alkyne, and this becomes the pathway. All right, so I cleared this up, I think, on the next slide here. We've said our full calculation says we have this three-membered iron metallocycle that nobody's ever seen before. And now we oxidize it with the use of the morpholine oxide. We lose, we have 1, 2, 3, 4 carbon monoxides, right? We lose one of them, that's carbon dioxide, we burn it off. And now we only have 3, but now iron is a 16 electron coordination complex, not 18. So it has a vacant orbital, a vacant site. And that's what binds the alkyne. Here's that binding. And now that goes on and finishes out through insertion reactions, and there's some back bonding there I won't talk about, but that goes on and makes the product. Okay, one last thing about that, this business. None of the organic chemists, and certainly very few of the inorganic chemists, had thought about the stereochemistry around the metal. Doesn't matter, and it does. There are several arrangements, there are 2 arrangements that you can have with regard to where you place the COs, the carbon monoxide around the iron. Here in B, I'll start with that because it's easy to see. The iron cyclopropane is on this side, going over there to your left, and over here to the right, that's the bonding of the triple bond containing compound, alkyne. And the COs are in a plane coming out of the screen at you. You all see that? Right? That leads to no reaction. But this is the guy where all the reaction occurs. The reaction that bonds between 2 and 4 happens because all these COs, there's 1, 2, and the other one is 3 down here, are all arranged in what they call a piano stool structure. Okay? Think of 3 legs of a piano stool. That's the way they sit underneath the iron. And then, as I've structured it up here, the 2 carbon ligands of this the cyclopropane and this the alkyne are on the top, kind of as the wings of a butterfly. And it's not surprising then that C2 and C4 get too close together, and when they do, they make a bond. Right? Okay, so this means we can combine these 2 new reactions I've just described. 2 new reactions discovered by one student. The first one was his coupling reaction. I call it a Stille coupling of this propargyl stannane that made the allene. And the second one, this 2 + 2 + 1 cyclization. And look at these incredible molecules that you can make in just 2 steps. Pretty amazing. Right? So are we ready to go on and try our natural product? Let's see how that works. Well, we're going to start with this known aldehyde over here. This is actually, we make it via the Myers asymmetric alkylation reaction. You don't need to know that. It's a pretty simple compound to make. Remember that it's optically active at that position. We made 1 enantiomer, all right? And now we're going to go through what we call a Corey-Fuchs reaction, where we make a double bond containing 2 bromides. We eliminate with then do lithium and quench with paraformaldehyde. That makes it go to just alcohol following it. None of that's all that important to you except to know that right here in this last step, we treat the carbonate from the alcohol with the tin chloride and this titanium and Grignard mixture. This is a reduction reaction that leads to an alenal titanium species that then alkylates, displaces the chloride from trying to give the chloride and makes the propargyl stannane. This is a really reliable reaction. We found one example of it in the literature going back to 1998. It's the only example. And it's turned out to be really successful for us. Now, we want to do our coupling reaction. So here's the propargyl stannane, and here's the iodide, this time of a fairly complicated structure, a substituted oxazole, as we call it. And the oxazole has, this is the 2 position, so it has a phenylthio group here, and at the 4 position it has a bromide, and at the 5 position it has an iodide. And the question is, well, where will the palladium insert? Can we know that? And it turns out, nobody'd ever known that either. And this is pretty fundamental, because oxazoles are widely used in medicinal chemistry and in agrochemistry, agricultural chemistry. They use these things because when you're making things that are peptide-like, remember, we want medicines that go in our bodies and do things like peptides do, but we don't want them to be peptides, because if they're peptides, we have to give them by injection. They can't survive the stomach acid. So the design then for lots of people who do medicinal chemistry is to design a drug that looks like a peptide but isn't a peptide, right? And one of the things they like to do is replace all the phenylalanines. So you know phenylalanine has an aromatic ring in it as the amino acid, right? And they replace that aromatic ring with a heterocycle because it's more water soluble and it's less prone to oxidation in the liver. So when you make a drug, one of the things they worry about is oxidation of a phenyl ring, an aromatic ring, by liver enzymes, because those things often are carcinogenic later. So they want to avoid just a benzene ring on a drug. So this becomes a really hot issue then for medicinal chemists. And now we have a way, well, you see it, I don't have to even talk about it. We can make an allene, and nobody's ever made that before either, because all the other literature used metal carbonyl derivatives, I'm used metal carbonyl derivatives here that would bind that basic nitrogen, right? And we can make an allene with functional groups on it, bring it forward through the reaction of the alkyne with the iron dicarbonyl now that goes and stitches up, not only from the allene, but through the alkyne, this 6,5 ring system, okay? So, wow, we've been able to do a lot of work. We're really pretty close to making the natural product now. We just have to close up this aromatic ring here and deliver on what I call the tail portion, part of the natural product. Okay, so just review. I put this in just because some of you, I don't know, probably I may have lost you at this point. Right? What is this guy talking about? But the idea is that we can take an allene and an alkyne, we can throw in iron carbonyl, and the iron carbonyl doesn't get caught up with these other groups that are on this heterocyclic ring, including the basic nitrogen. Instead, it makes a 3-membered metallocycle that loses CO, engages the alkyne, and closes and makes the 5,6 ring system, 2 rings at once in one reaction. All right? So now we got to do a cyclization. And when I think about every event in a reaction, what I like to do is I get to here and I have this material and I say, okay, give me a blank piece of paper. And now I'm going to start with that material in the upper left-hand corner of the paper and figure out what can I do with it? What could I predictably assume to be its character in terms of being able to go and make a ring system, a cyclized ring system in this area. And I'll show you the plan. The plan was that we could first do a condensation reaction right here that would engage and make this alpha-beta unsaturated system that you see here. This is nothing more than an aldol condensation. You've probably seen that in your organic classes. And then we thought we could use this bromide to do what's known as a Heck cyclization. Professor Heck was a famous professor at the University of Delaware who discovered these palladium catalyzed processes, actually won the Nobel Prize for it. And so we thought, well, we use that reaction to close the ring system, eliminate the bromide, and that'll give directly this material. And then I started thinking, well, what if that doesn't work? And Mike can also tell you, I'm a worrywart. So I'm hopeful, but I also know I need backup plans. Scientists need backup plans because lots of things you try aren't going to work. And so my backup plan was, I knew that this hydrogen, HA, was acidic, and you could remove it with bases. And if you did, this oxazole ring would temporarily open up and make an enolate. And if you had an enolate and this alpha-beta unsaturated ketone were in place, maybe that would do a conjugate Michael reaction, a conjugate addition eliminate HBr, and I'd still be able to make, well, you guessed it, the compound I really want to make down here at the bottom of the slide, right? Well, we had trouble with both of these groups, and nothing seemed to work. So this kind of summarizes some of those problems. We made this as a model study, and then we did everything to it. With X's bromide, we threw in the palladium. No cyclization took place. We got lots of strange looking products. And ultimately we decided the thioether at Y, that's a problem. And in fact, in one case, we actually found out here in yellow that when we use this palladium catalyst and this vinyl stannate, that the coupling happens here. No reaction happens at the bromide. And so we could actually use that reaction because then this palladium catalyst using sodium formate does a reduction of Y from S-phenyl to H. That's here, right? So that's the new compound. That worked in about 73% yield. And then we said, well, okay, let's try and use that now. And that still gave us lots of spots. You know TLC, right? Does everybody know what TLC is? TLC are your eyes in the reaction. Because you don't know what's happening in that flask. You know? Mike will also tell you I'm famous for quotable quotes. And one time I had a young person, a new graduate student, who set up his reaction. He had everything in the flask. He had the condenser over it. He had it under argon. It was stirring. And he was sitting on a stool watching it stir. And he sat there for an hour or so, and I made my way through the lab, and then later I came back, and he was still sitting there. He hadn't even moved. And I said, you know, you're not married to it. You can leave it, come back later. Whatever's going to happen in there, it's out of your hands, right? And then I told him about TLC. Well, TLC means you put a little bit of it on the bottom of a silica gel plate, and you develop the silica gel plate, and you look for where the starting material is disappearing, where the new spots maybe are happening. And in our cases, we saw in many of these reactions too many spots, too complicated. We need this to go to maybe 1 or 2 spots, but not 6 or 7, right? A hint about what was happening out of the reactions, however, and that led us to fix it. We're going to fix the root. So now, I've just taken you through 5 years of Akshay Shah's life, right? And this is the net result of it, right? The net result was he started with this compound right here as the ethyl ester and converted it into what we call the Weinberg amide. And now we use that for addition of Grignard, and then a reduction, and then a protection. MOM is an acetal, just a protecting group. And it's a nice series of letters. Organic chemists they like to use letters, and MOM makes us feel good, you know. So we use MOM, but it's an acetal, so we can easily remove it later in the synthesis. And then we deprotonated this hydrogen with LDA and quenched with this TIPS triplet, and that installed the triisopropyl silyl, that's what TIPS means, at that position. And then we deprotonated again, this time removing the hydrogen here at 5, and replaced that with iodine, NIS, right? We got the corresponding iodide there. And now we're ready to do our coupling with, well, there's the propyogenic stannate we made before, so let's couple it with the palladium catalyst we made, and sure enough, it works. 76% yield, that's pretty good. Made the alene, and 3 more steps, we installed the alkyne. We are now rocking, rolling system, okay? So well, we add our iron carbonyl, it stitches up the 2 rings at once, 61% yield. I'll take that. We remove the MOM group. Goodbye, MOM. We do an oxidation. The oxidation gives us the corresponding ketone. There's the ketone. And we throw in base, potassium t-butoxide. Well, now potassium t-butoxide, that pulls off a really acidic hydrogen here, and that condenses. And I teach all of my organic graduate students to count to 6. Right? 1, 2, 3, 4, 5, 6. So closing a 6-membered ring is an easy thing to do. It closes, it eliminates, and it makes this fully substituted aromatic ring that you see here in front of you. Now we have to reduce that, and the numbering might not make any sense to you, it doesn't have to. It's just that Rodriguez numbered the natural product, and this is his numbering, where that's C4 of his natural product, and that's C11. And to get to where we need to go, we need to add a hydrogen at 4, and ultimately we need to add a methyl group at 11. And we found that we could do this using a hydrido-copper complex. And we tried one that was invented by Buchwald at MIT, and it worked pretty well, but it was rapid as a reaction, but it gave us the hydrogen up and the hydrogen down both as a mixture of diastereomers, and then you have to separate those, and there was a difficult separation. I think the ratio was about 70-30. And so we wanted to do better than that. So we invented our own chiral ligand for the copper. There's the copper chloride, and this is the source of the hydrogen that makes the hydrido-copper complex. And, well, not me who did this, Akshay did this on his own. He came up with a much better ligand that gave us a better performance, so that we got an 89-11 ratio, or 86-14 ratio of isomers. And now, with a little bit of purification, we could get basically one compound that we could use for later. And he liked this reaction so much, he used it again, except not with the chiral ligand, this time with an achiral substrate. Here's a hydrido-copper. This one has been reported by Bruce Schutz at the University of California, Santa Barbara, and works extremely well. Rolls right on, gives us a 76% yield of the methyl group at C11. So we first introduce a methylene and then do a conjugate 1,4 reduction of the methylene, and we get a single stereoisomer at C11. And then finally, well, we're almost there. This is so close. You know, when I have a graduate student, they hate you. I mean, they hate me, I should say, at this point of the synthesis, because usually I just wander through the lab a couple of times a day. But with Akshay being this close, knowing that he was maybe 2 steps from the end, I was in there every 45 minutes. You know, it's like waiting for a baby. Is it there yet? Is it there? Anyway, he tried this reaction where he transmetallates from the iodide to the lithium reagent and added it into the ketone, and it worked really well. And you know, you may not remember now, but all we have to do to make the natural product is to remove this oxygen, this alcohol, and make that a hydrogen instead. And there's ways to do that. There's recipes in the literature to do that. Recipes. None of them work. No, we could never do it. That's why they call it research. You don't go to the library to look it up. You should have fun with all your friends and because they say, I'm going to go write a research paper. I'm going to go to the library and look up a bunch of stuff that's already known. That's not research. Discover something that isn't known. Tell me something I don't know. Right? Well, in this case, it was an unpleasant surprise. Oops, can I do 2? Okay, so here's the completion of the synthesis. We found out that what we had to do is add the sulfurylate ketone at 10, and that delivers, by rearrangement with indium trichloride at minus 78 degrees in this warming to room temperature, the aldehyde at 12. I'm not going to go into the details of that, but it starts out by the epoxide. You make the epoxide first, and then the indium chloride does a rearrangement with the epoxide. And from there, we use the recipe. Now we're home free, because this is a well-known reaction. It's called the Massimo-Rauch reaction. It's actually a revision of the Horner-Evans reaction, which you know from your software organic work maybe, which makes a double bond from the aldehyde here in a trans fashion to deliver the alpha-beta unsaturated ester. And that was really easy. And then the last step is just addition of methyl lithium to the ester, 2 equivalents. We had to use 3, remember, because this is an acidic hydrogen, so it's coming off anyway. We pull that off, but 2 methyl lithiums add in here, and then when we quench, the hydrogen goes back on to the oxazole, and sure enough, that material is identical to the natural product. Okay? So that's how we finished that compound. Now, how much time do we have? As much as we want. I'll do this really fast. So the new stuff I'm just gonna share with you is, and to be really fast about it, I'm not even gonna say the name. You can practice on the name yourself. There's a whole bunch of these metabolites, 4 of them, that you see here. They're all known from the fruit bodies of a mushroom. So that's how they were first isolated, by a German group, actually, in 1995. The references are down here. But it turns out that they first thought that these were really interesting antibiotics, and that's what I have as a bullet point, second one down. Nobody had ever seen these types of molecules before as antibiotics, so they're a new type of structure. And there's actually, unlike my early career in the 1980s, when our National Institutes of Health said, we don't need any stinking antibiotics, we have all kinds of antibiotics, right? Now suddenly they realize, uh-oh, all the penicillin doesn't work anymore for 92% of Americans. Penicillin does not work. Hmm? Yeah, it's become a hazard because, and the worst part is, the worst place to go in the world is a hospital, right? Because all the hospital infections, that's where the really ugly bugs grow, right? So now we're suddenly in need of antibiotics. And we keep, this is a war against the microbes. I'll tell you this, you probably don't, because we use the term antibiotic way too loosely, but it's defined really rigorously. An antibiotic is a substance produced by one microorganism to kill off another microorganism. They build colonies, and they don't want the microbe moving into their territory, right? So that's why microbes make antibiotics. And we as humans, we just use them, right? Because we can.